All right. Essentially, let me just write it down here. So if for I equal to 0, n, in this case, n equals to 3, integration of dphi dx, du dx equal to vi times f dx. Then for any coefficient v0, v1, etc., vn, integration of dv dx, du dx would be equal to v, integration of v times f dx for v of x equal to summation of I goes from 0 to n, vi of x. Do you agree? I mean, we're just multiplying each of these equations by vi and add them together. Because of linearity of the integral, we can basically take the linear combination from outside the integral to into the integral. And because of the linearity of the derivative, right, we can just take the linear combination from outside the derivative to into the derivative. So we get the v's. All right. Does that make sense? All right.
Yeah.
Okay, good. So that means we actually derive a linear system. We are deriving a linear system because we have actually 4 equations to enforce, right? For respectively for v equal to phi0, phi1, phi2, and phi3. We have 4 equations. And we have 4 unknowns because the solution u can be represented as a linear combination with 4 unknown coefficients. So that gives us 4 equations, 4 unknowns. Okay, so let's actually write down these 4 equations here. These 4 equations are actually for n equal to 3, that's basically n plus 1 equations, right? So we're just going to write it down here. Actually, it's a little bit less than n plus 1 equations because I only need to enforce it for phi1 and phi2 because phi0 is actually gone, right? Phi0, because I remember we already have certain boundary conditions, and the effect of the boundary conditions is to actually further reduce the degree of freedom, both for u and for v, right? So essentially, I know already my u0 is equal to 0, my u3 is equal to 0. And also for linear combinations to obtain v, I know my coefficient on phi0 has to be 0, my coefficient on phi3 has to be 0. So I only get, I only have actually 2 degrees of freedoms. So basically, I only need to enforce equation. So because of boundary condition dictates that u0 equal to un is equal to 0, okay, and v0 equal to vn equal to 0. So only need to enforce it for I equal to 1 to n minus 1, the integral from 0 to 1 of d phi dx times d dx of u. And here, let's actually expand u into its linear combination form. I equal to 1 to n minus 1. Remember, I equal to 0 and I equal to n. We have 0 coefficients. ui, well, let me don't confuse ourselves with duplicate indices. So we already used I, so let's say this summation we use j for now. Okay, so here would be, I'm representing my u as a linear combination of uj with vj's. Okay, this would be equal to integration from 0 to 1 of phi I times f. Now it's very clear that we have 4 equations and 4 unknowns. Not 4, 2. I mean, when n is equal to 3, then we have 2 equations, 2 unknowns. Basically, we have, in general, we have n minus 1 equations, n minus 1 unknowns, right? All right. So let's actually expand this further. Because this linear combination can also be taken out of the derivative and then taken out of the integral, this actually becomes summation from j goes from 1 to n minus 1. Also, uj can be taken out of the derivative because uj is a number, right? It's not a function. It can be taken out of the derivative and taken out of the integral. And the integral becomes integration from 0 to 1, the derivative of I times the derivative of phi j. Okay? And this is phi I f dx. All right. Look at what this is. Remember, phi is something we have already drawn, right? Phi is a known function. Once we know the grids, once we know how the elements are distributed, we know exactly the function form of phi I, phi j. So this is something we can already pre-compute. So let's just call this aij. Again, we know what phi I is, we know what f is. F is the right-hand side of the differential equation, right? It's a given function. We already said that. Like f is a given function right in the beginning. So we should be also able to compute this. And let's call this bi, right? For every I, this is a different number. Now, what do we have? We have a matrix, right? We have a matrix A11, A12, etc., A1 n minus 1, A21, A22, etc., right? A n minus 1, 1. So we got a matrix times these unknown coefficients, U1, U2, etc., to Un minus 1 is equal to my B1, B2, etc., to Bn minus 1. So if I can solve the linear system, we get the U1, U2 to Un minus 1, the linear combination coefficients to the known basis functions, the head functions. And we can recover what the solution to the differential equation is.